In the previous video, we discussed Chebyshev rule, and Chebyshev rule told us how much data we can expect between the two standard deviations away from the mean, one standard deviation away from the mean, or three standard deviations away from the mean. In this video, we're gonna talk about a specific distribution, which is a normal distribution. And let me remind you what a normal distribution is. First of all, normal distribution is symmetric. Number two, it is bell-shaped. And what that means is that the majority of the data is located in the center or around the mean. So this is our mean. This is mean plus one standard deviation, mean plus two standard deviations. So these marks 1 and 2 mean the standard deviations away from the center. Okay, so the Chebyshev distribution is too rough for this distribution. We could approximate the data values more exact with the normal distribution. So the empirical rule says that if we're looking at a normal distribution, then we can expect 68% of the data within one standard deviations from the mean. And we can expect roughly 95% of data within two standard deviations from the mean, and 99.7% of data within three standard deviations of the mean. That's an improvement upon the Chebyshev theorem. Now, again, I want to reiterate that these percentages apply only to the bell-shaped curve. All right, so here's an example of an application of the empirical rule. We know that the SAT scores from students in new test preparation course had a mean score of 1,150 and a standard deviation of 150 point units. So what that tells us, or points, what this tells us is that 68% of the data of the scores are going to be between 1,000 and 1,300 points. And then the 95% of all of the scores are going to be between 850 and 1,450 points right here in this bigger interval. And then the rest are going to be from 700 to 1,600 points. Now, what this is going to tell us also, if we have anything less than 700 and more than 1,600, that's going to be an outlier. That would be a very, very unusual value. Now, if we get something below 850 or above 1,450, that's going to be an unusual value. So if it's going to be below 850, that's going to be unusually low value. And if we get something above 1,450, that's going to be unusually high value. So now let's go ahead and practice how to draw a bell curve or a normal curve for any mu and sigma. So first of all, we're gonna mark our line with mu in the center, and then we're gonna mark 3 equal steps to one side and 3 equal steps the other side. So 1, 2, 3, and 1, 2, and 3. Okay, so this is going to be mu plus 1 sigma, mu minus 1 sigma, mu plus 2 sigmas, mu minus 2 sigmas, and finally 3 sigmas. Okay, so we know that very little data is going to be, beyond the 3 standard deviations. So we're going to draw a line here almost, at our number line. And then when we approach to now here we're going to increase our slope a little bit so that we're going to have a little bit more data here. And once we reach this 2 standard deviations away from the mean, we are going to increase our slope even more, like this. And then we know that the 68% of the data are going to be within 1 standard deviations away. So we're going to just finish it with a top of the bell. So this is how you would draw a bell curve. Okay, so now let's specify the mean and the standard deviation. Let's say we have a distribution with a mean of 50 and a standard deviation of 10. Again, I'm gonna put down the center, 50, and I'm gonna also do the 3 equal intervals to both sides of 50. All right, so I marked the number of standard deviations away and the actual numerical values with those points equal to. So again, we're gonna start the 3 standard beyond the 3 standard deviations away, we're basically on the line, right? And then coming to 2 standard deviations, our slope is increasing slightly, and then coming closer to the center up to 1 standard deviation away, our slope is going to be increased even more. And again, our distribution is symmetric, so it should be similar on both sides. And then we're gonna finish with a rounded top. So in reality, these are like very smooth. That shape is very smooth. There are no angles, but we're just approximating. Okay, so if we apply the empirical rule here, we know that 68% lies within 1 standard deviation, and because of the symmetricity, we're going to have 34% in here. This piece is 34, and this piece is also 34, right? Further away, we're going to have 13.5 and 13.5. And then the rest is 2.5 on each side. Okay, if we want to be exact, these little ones right there beyond the 3 standard deviations are going to be 0.15%, and these inside are going to be 2.35, but I basically combine them together into 2.5% in each tail. So again, let's recall about our unusual values and outliers. So your unusual values are going to be beyond those points. So the ones that I circled, those are unusual values, unusually low and unusually high. And anything lower than 20 and higher than 80 would be an outlier. Now, this picture illustrates how standard deviation determines the shape of the distribution. All three of these bell curves, they have the same mean of 1,000. Only one, the blue curve, it has a standard deviation of 80. The red one has a standard deviation of 120, and the yellow one has a standard deviation of 190. So you can see how when the standard deviation becomes larger, your distribution becomes wider and not as tall. The distribution with the smallest standard deviation is the tallest, and it's the skinniest. So this is how the standard deviation influences your bell curve distribution. Here's an example that will help us to practice this. Approximate the mean and standard deviation from a graph of this normal distribution. So the mean is the value in the center. So the mean is 50 here. Now we know that 3 steps away, we get to the flat side of the of the distribution. So this is mean plus 3 standard deviation. So it's 50 plus 3 standard deviation, and that equals to 92. So let's solve this equation by subtracting 50 on both sides. We have 42 equals 3 standard deviations. So 42 divided by 3 is going to equal 14. So 42 divided by 3 is going to be 14. So our standard deviation for this distribution is 14. We could check if we get, this is mu minus 3 standard deviation. So 50 minus 3 times 14 is going to be 8. I believe it will. All right. So, and another example says, using empirical rule, aluminum cans with thickness of 0.0111 inch have exile loads with the mean of 281.8 pounds. So mean is 281.8 pounds. And a standard deviation of 27.8 pounds. The exile load is measured by applying pressure to the top of the can until it collapses. Use the empirical rule to find the minimum and maximum usual exile loads. Okay, so remember that all usual values are located within 2 standard deviations. So 1, 2. This is mu plus 2 sigma. So we have 281.8 plus 2 times 27.8. Sorry, it is 27.8. And we come up to 226.337.4 on the right side for 2 standard deviations to the right of 281.8. And on the other side, it's mu minus 2 sigma. So we have 281.8 minus 2 times 27.8. And that will give us 226.2 pounds. So the usual values are the values between, for the exile loads, are values between 226.2 and 337.4 pounds. And the next question is, one particular can had an exile load of 504 pounds. Is that a significant value? Is it an outlier? So 504 is way out here on the scale, right? It's way greater than 337.4. So the answer is it significant value? Yes, it is, because it's way beyond the 2 standard deviations away from the mean. Is it an outlier? Remember that outlier is more than 3 standard deviations away. So let's figure out what would be mu plus 3 sigmas away. So that's going to be 281.8 plus 3 times 27.8. And that value comes out to be 365.2 pounds. And of course, 504 is way above 365. It's way above 3 standard deviations from the mean. So yes to both. It is a significant value and it is an outlier.